So this week is going to wrap up the seminar, and it's going to have a particular focus on the distinction between frequentist versus Bayesian methods. The lecture notes are going to have 4 sections plus an appendix. First section is going to be a representation that the frequentists give us the probability of the data conditional upon the parameters, whereas the Bayesians give us the probability of the parameters conditional upon the data. To illustrate this difference, I'm going to use frequentist p-value, compare it with the Bayesian posterior, but it's worth noting that this comparison is not a direct comparison of this versus this per se. Rather, it's a comparison of a particular frequentist method, the p-value, versus the Bayesian posterior, but I want to do it because p-values are quite commonly used in our statistical analysis. So, although this doesn't provide a direct comparison of Bayesian and frequentist methods per se, when we look at the difference between the frequentist confidence interval and the Bayesian credible interval, this will be a direct comparison of frequentist and Bayesian methods because they're both attempting to calculate an interval. And then we're going to go over some additional applications of Bayes' theorem. And we saw that one really important use of Bayesian theorem was to give us hierarchical models that would enable us to tease out underlying processes. But there's a wide range of additional applications. I'm just going to go over a few to give you a flavor of the possibilities. So we've got Bayesian networks. We can combine the Bayesian posterior with loss functions to help us make decisions. And then there's this third one, and this third one is actually of some practical importance because increasingly there's becoming available packages in R that do Bayesian analysis running in the background, but they do so with far simpler code that's involved with runjags. And the particular package we're going to look at is one that's called BRMS. And the advantage of looking at something like BRMS is twofold. First of all, when we went and talked about our hierarchical models, those are particularly relevant when you've got observational studies. So we observed the number of offspring produced by any one bird. We observed the bird's age, the bird's territorial size. That was an observational study. But many of you will be doing designed experiments that are going to have blocks, going to have plots. You're going to impose treatments, likely under controlled conditions. You're going to compare those treatments. So for experiments such as this, BRMS is going to be a really simple way to analyze those data using Bayesian methods. The second reason I want to go over BRMS is that with many of these packages, you're going to see them and they're going to be tempting to use because, like BRMS, they've got relatively simple code. They've got simple code and they also can be very powerful. So, for example, we're going to see that BRMS may be more powerful than some of the packages that you're already using to run frequentist analysis. The problem is that these sort of packages can also be dangerous because unless you're extremely mindful about what you're doing, it's quite possible to obtain plausible yet erroneous results. And then finally, summary and conclusions. I want to go over what I consider to be the 3 big differences between frequentist versus Bayesian methods, and then revisit the vision that I had for this seminar and what I hope you got out of it. So let's go back here and think about this notion that frequentists give us the probability of data conditional upon the parameters, and let's think about how the frequentists might calculate a p-value. And so the example that I'm going to use is that we have a research hypothesis. And the research hypothesis says that the mean IQ of international baccalaureate students, IB students, is greater than 100. So that's the research hypothesis. So the first thing that the frequentist does, if they're going to do try to come up with a p-value, is that they posit a null hypothesis that contradicts the research hypothesis. So the null hypothesis is not that the IQ is greater than 100. The null hypothesis is the mean IQ is going to be equal to 100. And then they go out and collect some data, sample size of 9. They observe an average IQ of 111 in that sample. Then they make a couple of additional assumptions. The first assumption is that IQ of the IB students is normally distributed. And secondly, the standard deviation of that normal distribution is equal to 15. This particular assumption is not necessary if I want to illustrate the ideas behind the p-value. On the other hand, by using an assumed standard deviation, it relieves me of the responsibility of using a t-test that simply makes this explanation a lot simpler. So, what we have right now, based on our null hypothesis, is that the IQ of IB students is normally distributed with mean 100 and standard deviation 15. So, there we have it. There's all individuals in the population, normally distributed, mean 100, probability density shown on this axis, and sigma is equal to 15. Now, let's pretend I could go out there and I could take a sample of size 9 from that normal distribution and calculate y bar 1. And I go out, I could take another sample of 9 from that distribution, get y bar 2, continue that process until I had an infinite number of sample means based on sample sizes of 9. And then I could obtain the probability distribution of these sample means of size 9, and there it would be. And this is referred to as a sampling distribution because it's the distribution of a sample statistic. It's the distribution of all sample means of size 9 taken from the underlying population. And so I've just reproduced it here. Now, what the mathematicians tell us is that they know with absolute certainty that if the underlying population is normally distributed with some mean mu and some standard deviation sigma, then if you can consider all possible values of y bar, all those means are going to be normally distributed with mean mu, but the standard deviation is going to be reduced sigma over root n. So if mu was 100, based on a null hypothesis, we assumed sigma was equal to 15. Our sample size was 9, so all possible samples of size 9 taken from this presumed underlying distribution would be normally distributed with mean 100 and standard deviation 5. So there's our sampling distribution, normally distributed with mean 100 and standard deviation 5. There it is right there. What we obtained was an average IQ. Our average IQ was 111. So we can calculate the probability of getting an average IQ of 111 or more by using this code. So there's our 111. The mean, according to our null hypothesis, is 100. The standard deviation, we decided was 5. We use lower tail equals false because we're looking at the area in the upper tail. And what this R code returns is this value here, and this is our p-value. And the letter P stands for probability because this is a probability. It's the probability of getting an average IQ of 111 or more based on sample size of 9. Now, this is a very small number. This is a very small number that is quite implausible if our null hypothesis was true. So the fact that we've got a very small number here serves as strong evidence that the null hypothesis was wrong, and therefore the research hypothesis was correct. A few other things to point out about the p-value. First, if we scoot back up here, it gives us the probability of the data conditional upon the parameters. So it's the probability of the data conditional upon the parameter, which in this case is going to be mu. So we conditioned upon the parameter. The mean IQ of the IB students was equal to 100. The probability of getting the data was an observed IQ of 111. So this p-value is the probability of the data conditional upon the parameters. The second thing is this whole process is rather indirect. So we started off with a research hypothesis. We posited a null hypothesis that contradicted the research hypothesis. We got some data. We got a p-value of 0.0139, which is implausible if the null hypothesis is correct. So we've got strong evidence that the null hypothesis is incorrect, and that serves as strong evidence that our research hypothesis was in fact correct. So to me, that seems a rather indirect approach. And the third thing is that the p-value of and by itself provides only a little information. What does this p-value of 0.0139 represent? It's the probability of, or let me put it this way. It's telling us that there's only a very tiny probability that the true mean IQ of the IB students is equal to 100. So we're pretty darn sure that the mean IQ of the IB students is greater than 100, but other than that, it doesn't provide very much information. So what we're going to do, or what I'm going to try to do, is show that in general, the Bayesian posterior is superior to the frequentist p-value.